All right, welcome back to the deep dive. Today we're going to be tackling a question that I think has probably crossed all of our minds at some point, especially when we find ourselves looking up at a skyscraper or maybe hear about a bridge collapse in the news.
It definitely gets you thinking about what keeps these structures up.
Exactly. Why do buildings sometimes just fail?
Yeah, it's a fascinating question, really. It's all about this balance we strike between human ingenuity and just the sheer power of nature and the physical world around us. I mean, think about it. The buildings we live in, work in, the bridges we drive over, they're all testaments to how much we've learned about engineering and design. But it's those moments when things go wrong, those failures that teach us some of the most important and sometimes, unfortunately, the most tragic lessons.
I totally agree. And to really dig into this whole topic of building failures, we've been looking closely at this book. It's kind of the go-to book on the subject, I think. Why Buildings Fall Down, How Structures Fail by Mathis Levy and Mario Salvadori.
Oh, yeah, I know this one. Great cover, too. The one with all the kind of like vectors of force on those, what are they, girders?
Yeah, beams, I think.
Yeah.
Just showing those forces.
Yeah, really gets the point across.
It does.
Yeah.
So our mission today is to, kind of pick out the essential, like the key insights into the science behind these failures. Like what can we learn from them? We want you to walk away really understanding those forces that are always at work.
Mm.
And most importantly, those lessons we've learned, sometimes the hard way, about why buildings fall down.
Yeah.
So where should we start? Like, how can we even begin to understand why a building might suddenly collapse?
Well, I think the most logical place to begin is by thinking about those fundamental forces that are constantly acting on every single building, no matter how big or small, where it is. And the most obvious one, the one we experience every moment of our lives, is gravity.
Right. It's always there.
Always there. And it creates what we call a vertical load, that constant downward pull.
So the weight of everything, basically. But the book makes a distinction between different types of vertical loads, right?
Absolutely. There's this key difference between what we call dead loads and live loads. Dead loads are the weight of the building itself. All the materials, the concrete, the steel, the roof, the walls, even the permanent fixtures like plumbing and things. That's all the dead load.
So the constant, unchanging weight, the stuff that's always going to be there.
Right, exactly. Live loads, on the other hand, those are much more variable. They depend entirely on how the building is actually being used. So think about the people inside, the furniture, any equipment, even things like, snow piling up on the roof in the winter.
Oh, wow. Yeah.
All that contributes to the live load.
So it's not just about how much the building itself weighs, but also how it's going to be used and all the stuff that can be put inside it.
Right, you have to consider all of that when you're designing a building.
That makes a lot of sense. But it's not just about things pushing down,
Mm.
right? What about the forces that come in from the sides, like wind? I mean, we've all seen how much wind can affect even large buildings.
Yeah, you're talking about horizontal loads, and those are just as critical to consider in structural design as the vertical loads we talked about. Wind is a major factor, especially as buildings get taller.
And I guess it's not even just like a steady push, is it? It's more complicated than that.
Much more. Wind can create all these different areas of high pressure on one side of a building and then suction on the other side. So it's this really complex set of forces that the building has to withstand.
Wow. Yeah. That makes sense.
And there have been some pretty tragic building failures throughout history because of wind. Really highlights just how crucial it is to get that design right, to be able to really accurately predict and withstand extreme wind events. I mean, in a lot of cases, those failures are what led to some really big changes in building codes, to make sure that kind of thing doesn't happen again.
And then, of course, there are earthquakes, which is a whole different kind of sideways force, right?
Yeah, absolutely. With an earthquake, you're not talking about wind pushing on the building. It's the ground itself moving underneath it.
Right. And that creates those, what are they called? Inertial forces.
Precisely. Because a building has mass, it wants to resist any sudden changes in motion. So when the ground shakes rapidly during an earthquake, the building kind of tries to stay put, because of its inertia. And that creates these really strong horizontal forces that can act on the entire structure.
So the ground's moving one way, the building's trying to stay put, and that puts tremendous stress on everything.
Exactly. And the problem with earthquakes is that those forces can be so unpredictable, coming from different directions with varying intensity. That's what makes designing for earthquakes so challenging. A lot of early buildings in earthquake-prone regions, they didn't really account for these forces adequately. And sadly, their failures were what showed us the importance of having flexible connections and systems that can dissipate energy during an earthquake.
Right, so the building can kind of move with the ground instead of just rigidly resisting it.
Right, that's the key. And it's important to remember that all these loads, whether it's the vertical pull of gravity or the horizontal forces of wind or earthquakes, all of that has to be transferred safely down to the ground through the foundation.
Right, so it all ends up there.
It all goes there. The foundation's stability and its ability to prevent the building from settling unevenly are absolutely crucial. If the foundation fails, the whole structure can come down.
It's like the most important part.
It's the base of everything.
Okay, so we've talked about the different forces that act on buildings, but what about the materials themselves? How do they hold up against all that stress?
Well, that's where the properties of the materials come into play. Different materials behave in different ways when they're subjected to forces. We use two key terms to describe this: stress and strain. Stress is basically the internal force that's acting within a material per unit area, kind of like how much it's pushing back against the load. And strain is the deformation, the change in shape that happens in response to that stress.
Okay, so stress is how hard the material is fighting back, and strain is like if it starts to lose that fight a little bit and changes shape.
Yeah, you could think of it that way. Now, a good example is steel. Steel is a fantastic material for construction because it performs really well in both tension when you're pulling it apart and compression when you're pushing it together. Concrete, on the other hand, is very strong in compression, which is why it's so great for foundations and columns that carry a lot of weight. But it's not very good in tension.
Oh, right, so it's great at holding things up, but not so good at being pulled apart.
Right. And that's why you almost always see steel reinforcing bars, rebar, embedded inside concrete structures. The rebar provides the tensile strength that the concrete lacks. So together they make a really strong and versatile building material.
Makes sense. They kind of complement each other.
Exactly. And then, on top of those basic ways that materials can fail, there are other important failure modes, like buckling. Especially important for slender columns and beams under compression. Imagine pushing down on a thin drinking straw. It doesn't just squash down, it kind of buckles out to the side.
Right, it just gives way.
That's buckling. So
Yeah.
you have to consider the slenderness of a column or a beam and its cross-sectional dimensions to prevent buckling.
So it's not just about how strong the material is, but also the shape and how it's put together.
Right, exactly. And then there's another interesting phenomenon called fatigue. That's when a material fails, not because of one big load, but from repeated cycles of loading and unloading, even if the stress each time is below the material's ultimate strength.
So kind of like bending a paperclip back and forth until it breaks.
Yeah, exactly like that. Structures like bridges and aircraft wings, those experience these constant cyclical stresses, so they're particularly vulnerable to fatigue failure. And this highlights another important point about design. You have to consider not just the maximum expected load, but also those repeated stresses over the structure's lifespan.
So it's not just about one big test. It's about how it holds up over time.
Precisely. And there's one more type of failure we should talk about: creep. This one's a slow process. It's the gradual, permanent deformation of a material under a constant load over a very long time.
So it's not a sudden collapse,
Yeah.
but more of a slow warping or sagging.
Yeah, you can think of it that way. Creep can cause problems over time, especially in concrete or certain metals that are under constant heavy loads. It can lead to misalignments and eventually failures. So that's something that has to be factored into the design as well.
So even if a building is big to withstand the big loads, these smaller, more gradual forces can still cause problems over time.
Exactly. It's a complex interaction of factors.
Okay, so we've covered a lot of ground here. We've talked about the forces, the materials, and how they can fail. Let's get into some real-world scenarios now. Why do buildings actually fall down? What are some of the most common causes?
Well, according to the book, there are a few main categories. One of the most common is actually design errors.
Really? I would have thought that would be pretty rare with all the calculations and everything.
You'd think so, right? But it happens more often than you'd expect. It could be a simple misunderstanding of the loads the building will experience. Or maybe the calculations for how strong a certain element needs to be are just off. Sometimes it's even something as small as overlooking a crucial connection detail.
Wow, yeah. A small mistake can have big consequences.
Absolutely. And this is where the concept of redundancy in structural design comes in. That means having multiple load paths so that if one element fails, the others can still take over and prevent a total collapse.
So like having extra columns or beams just in case one of them fails.
Exactly. It's like a safety net for the structure.
Mm.
And historically, those failures where there wasn't enough redundancy, those have often been the most tragic.
Redundancy seems like a really important idea. So what about cases where the design is good, but something goes wrong during the construction?
Yeah, construction defects are another major cause of building failures, and this covers a wide range of issues. It could be poor workmanship, maybe the welding on a steel frame isn't done properly or the concrete isn't cured correctly, or maybe the contractors used cheaper, substandard materials to cut costs. All of that can compromise the strength of the structure, even if the design was perfect.
It's like having the best recipe in the world, but then using the wrong ingredients or messing up the steps.
Yeah, exactly. The best design in the world won't matter if the actual construction isn't done right. That's why things like skilled labor and rigorous quality control on construction sites are so important.
You definitely don't want any shortcuts there. So what about the ground beneath the building? We talked about foundations earlier.
Right, foundation settlement, that's another common culprit. If the soil beneath a building settles unevenly, it can create tremendous stress on the structure above. You can get cracks, distortion, and in the worst cases, the whole thing can collapse.
So if the ground's moving around, the building is going to have a hard time staying up.
Exactly. And that uneven settlement can happen for different reasons. Maybe the soil moisture content changes, or the soil wasn't compacted properly before construction. Sometimes seismic activity can affect the ground too. It's really crucial to understand the soil conditions and design a foundation that can handle them.
So there's a lot more to foundations than just digging a hole and pouring concrete.
Oh, absolutely. It's a whole science in itself. And then sometimes it's not about the design or the construction, but simply how the building is being used.
Right, like if it's overloaded.
Exactly. Overloading happens when you put more weight on a building than it was designed to handle. It could be too many people in one area, or maybe someone decides to store heavy materials on a floor that wasn't meant for that. Even something like a huge snowstorm can overload a roof.
So you can have a perfectly good building, but if you use it the wrong way, it can still fail.
That's right. Buildings are designed with specific load limits in mind, and exceeding those limits is always risky.
Makes sense. And then, of course, there are the forces of nature that we can't control, like those extreme weather events or earthquakes we talked about earlier.
Yeah, those are some of the biggest threats to buildings. Severe windstorms, hurricanes, tornadoes, those can generate forces that are far beyond what most buildings are designed to handle. And earthquakes, well, we already talked about how those can be incredibly unpredictable and destructive.
Right. Nature can be pretty unforgiving.
And even over time, normal wear and tear can take its toll. Corrosion, especially in steel structures, can weaken the material over time.
So even if a building survives the big events, it still needs to be able to stand up to the everyday wear and tear.
Exactly. And then, of course, there's fire. Extreme heat from a fire can weaken materials like steel drastically. I've seen some pretty dramatic footage of steel beams just twisting and collapsing in fires. It's a reminder that extreme temperatures can have a huge impact on structural integrity.
Yeah, that's a scary thought. And there's one more type of failure you mentioned earlier, progressive collapse.
Right, progressive collapse. That's when the failure of one element, maybe from an overload or an impact, triggers a chain reaction where other elements start to fail as well.
It's like a domino effect.
Exactly. One thing leads to another, and you can have a large portion of a building collapse, even though the initial failure was localized. That's why it's so important to design buildings that can contain those localized failures and prevent them from spreading.
So it's not just about making each individual element strong. It's about how the whole structure works together.
Right, the interconnectedness of the system is really important.
This has been really interesting, but it's also a little bit unnerving to think about all the things that can go wrong. It makes you realize how many things have to go right for a building to stay standing. So what role does maintenance play in all of this? I mean, once a building's built, how do we make sure it stays safe over time?
Regular inspections and maintenance are absolutely crucial for any building. Having qualified professionals come in and do checks, look for signs of damage, that can make a huge difference.
Sounds like a regular checkup for a building.
Exactly. They're looking for things like cracks, corrosion, water damage, any signs that the building might be settling unevenly. And the key is catching those problems early. before they turn into something serious.
Because a small problem today could become a big disaster tomorrow.
Precisely. Early detection allows you to address the issue before it escalates, to reinforce a weakened element or fix whatever is causing the damage. Think of it like preventative medicine for buildings.
It's a great analogy. So ultimately, who's responsible for making sure all of this happens? There are a lot of people involved in the life of a building.
It's a shared responsibility. You've got the engineers who design the structure, the architects who work on the overall form and function, the contractors who build it, and of course the building owners who are ultimately responsible for its upkeep. Everyone has a role to play in making sure things are done right and that the building remains safe. And then you have building codes and regulations that set minimum standards for design and construction. Those are crucial too to ensure a baseline level of safety.
So it's really a team effort from the design phase all the way through the life of the building. And everyone needs to be committed to doing things the right way, not cutting corners.
Exactly. It's not just about the technical aspects. There's a strong ethical component to building safety. It's about people's lives, their well-being.
And that's something we shouldn't forget.
Absolutely not. And it's worth noting that all those lessons we've learned from past failures, those have been instrumental in driving progress. Building codes get updated, engineering techniques improve, construction practices get refined. Every collapse, as tragic as it is, provides valuable insights that help us build safer and more resilient structures in the future.
So it's a continuous cycle of learning and improving. And it sounds like we've covered a lot in this deep dive.
We have.
We've looked at how those fundamental forces, like gravity, wind, and earthquakes, can act on a building. We've talked about how different materials behave under stress and how they can fail. We've seen how errors in design, construction, or maintenance can all contribute to building collapses. We've talked about the importance of regular inspections and that shared responsibility for safety. It's a lot to take in, but it's all essential for understanding why buildings fall down and what we can do to prevent it.
It really underscores just how complex the built environment is. All those forces at play, the different materials and their limitations, the potential for human error, it's a lot to consider.
Yeah, it is. But thinking about these things, even just being aware of them, can make a difference. It can help us ask the right questions, make better decisions, and ultimately create a safer world.
I agree. It's about being informed and being proactive.
And on that note, here's something to think about. As you go about your day today, take a look at the buildings around you, the ones you walk past, the ones you live and work in. Think about what we've discussed today. Think about all those unseen forces that are constantly acting on them and all the work that went into designing and building them. Does it change how you see those buildings?
It might make you appreciate them a little more.
Yeah, and maybe ask some new questions about how they're built and how they're maintained.
And those questions are good. They can lead to better understanding and better solutions.
So that's our deep dive into why buildings fall down. We hope it's given you a new perspective on the world around you, and maybe even sparked some curiosity about the structures we rely on every day. Thanks for joining us,
Thanks for having me.
and we'll see you next time on The Deep Dive.
See ya.